The cylinder reaches the limits of extension during the ongoing ramp down event, and flow slams to a halt, as does the applied load. Pressure spikes to that of the main pressure relief valve. Only after the ramp-up event has finally completed does the proportional valve fully shift to the closed center position. Again, we failed to meet all of our objectives during the extension phase. Yes, the applied load did accelerate smoothly, and yes, the rod fully extended. However, we failed to decelerate smoothly and slammed to a stop. Additionally, pressure spiked. The retraction phase is the same song, only played in reverse. When an operator presses retract, the coil of control relay CR2 is energized. The contacts associated with control relay CR2 immediately change states. Contact CR2A closes and establishes a holding circuit via the normally closed LS2 contact. This holding circuit allows an operator to release the retract push button. Simultaneously, contact CR2B closes and enables the negative ramp generator set to execute a slow 10-second ramp. Applied voltage to the linear force motor in the proportional valve does this super slow crawl from 0 to negative 10 volts over an agonizing 10 seconds. Slowly, 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 the spool is shifted into the cross-connect position. At a certain minimum voltage, the deadband is passed and the proportional valve cracks open, allowing a minimum amount of flow. Flow rate goes from 0 to the tiniest trickle. The cylinder and applied load slowly creep backward. This being said, the velocity of the cylinder and applied load steadily increase as applied voltage is steadily ramped to negative 10 volts and the proportional valve is progressively opened more and more. Let's say halfway through the ongoing negative ramp event, the cylinder extends far enough to hit LS1. No change in state is observed since normally open contact CR1A is still in the deactivated open state. Leaving the reset region of LS1, LS1 recloses. Another couple seconds later, the ramping event reaches full negative 10 volts and the proportional valve fully opens in the cross-connect position. Flow rate reaches a maximum and the cylinder obtains maximum retraction speed. However, let's say it only stays at maximum speed for the briefest of moments before the applied load strikes LS2. LS2 opens and the coil of control relay CR2 is de-energized. The contacts associated with control relay CR2 immediately return to their deactivated states. Contact CR2A opens and removes the holding circuit. Simultaneously, contact CR2B opens and signals the negative ramp generator to execute a 10-second ramp down. Applied voltage to the linear force motor slowly goes from negative 10 volts to 0 volts, and the spool is slowly shifted back to the closed center position. Flow is progressively decreasing, however the cylinder is still retracting. Leaving the reset region of LS2, LS2 recloses. No change in state is observed since contact CR2A is still in its deactivated open state. Flow and retraction speed decrease, however not fast enough since the cylinder is still moving at a pretty high rate of speed. The cylinder reaches the limits of retraction during the ongoing ramp down event and flow slams to a halt, as does the applied load. Pressure spikes to that of the main pressure relief valve. Only after the slow ramp up event completes does the proportional valve finally move back to the closed center position. The retraction phase is essentially a repeat of the successes and failures of extension. Yes, the applied load did accelerate smoothly, and yes, the rod fully retracted. However, we failed to decelerate smoothly and slammed to a stop. Additionally, pressure spiked. Again, here's what a simplistic graph of velocity and rod displacement would look like during the extension and retraction phases. Note velocity steadily increases during the constant acceleration phase produced by the ramping event. Once velocity reaches maximum, it levels out, but only briefly because the deceleration event occurs at partial extension. During the ongoing deceleration event, velocity immediately goes to 0 as the cylinder crashes to a halt. Given changing velocity during the constant acceleration phases, rod displacement position non-linearly changes. Once maximum constant speed has been achieved, displacement increases linearly. Again, this is an obvious simplification, but you should get the picture. The larger point is that the sudden transitions from a certain speed back to 0 is meant to imply that the deceleration is astoundingly abrupt. Note, we're assuming for our previous example that the ramping event is short enough and the cylinder travel length long enough that it actually does briefly obtain maximum speed given flow rate produced by the pump. If this was not the case, we might observe slightly different behavior. For example, consider a smaller diameter cylinder with a shorter travel length. At the current level of pump flow, one might observe this smaller cylinder to strike LS1 on extension before the ramp-up event has completed. In this case, we're assuming the ramp generator would immediately halt the ongoing ramp up and immediately begin a ramp down from this previously obtained voltage value. This would yield subtly different velocity and displacement characteristics. As previously, the ramp-up event is still way too slow, and despite a progressively decreasing flow rate, the cylinder is still moving at a pretty high rate of speed. The cylinder reaches the limits of extension or retraction during the ongoing ramping events, and flow still slams to a halt, as does the applied load. Long story short, back to the drawing board. Alright, no transition was an unqualified failure. Too long of a transition still produced some undesirable effects. Let's have yet another go. Let's dial the ramp generator transition time down to a relatively brisk 1 second. Again, this is an arbitrarily generated value for illustration purposes only. Starting from a fully retracted condition, when an operator presses extend, the coil of control relay CR1 is energized. The contacts associated with control relay CR1 immediately change states. Contact CR1A closes and establishes a holding circuit via the normally closed LS1 contact. This holding circuit allows an operator to release extend. Simultaneously, contact CR1B closes and enables the positive ramp generator set to execute a 1 second ramp. Applied voltage to the linear force motor does a relatively brisk transition from 0 to positive 10 volts over a snappy 1 second. During this short time span, the spool is progressively shifted into the fully straight-through position. Flow rate goes from 0 to maximum over the same time period. The cylinder and applied load don't jerk forward, however their acceleration is pretty abrupt. Let's say the ramp-up event is so fast, we're at maximum speed even before we hit LS2. The extending applied load hits LS2 2 inches into the 8-inch stroke. No change in state is observed since the normally open contact CR2A is still in the deactivated open state. Leaving the reset region of LS2, LS2 recloses. Another couple seconds later, 6 inches into the extension stroke, the applied load strikes LS1. LS1 opens, and the coil of control relay CR1 is de-energized. The contacts associated with control relay CR1 immediately return to their deactivated states. Contact CR1A opens and removes the holding circuit. Simultaneously, contact CR1B opens and signals the positive ramp generator to execute a brisk 1 second ramp down. Applied voltage to the linear force motor quickly drops from positive 10 volts to 0 volts, and the spool is progressively shifted into the closed center position over the same time period. Flow quickly decreases, and the cylinder and applied load slam on the brakes. Given the abrupt deceleration, let's say it comes to a halt just short of full extension. Our results during this extension phase are pretty mixed. Our acceleration and deceleration was a little too brisk, and the rod failed to fully extend, though these errors are not as egregious as previously. I think we are getting close, and one more adjustment might do the trick. Before doing so, let's examine the retraction phase. The retraction phase is the same song in reverse. When an operator presses retract, the coil of control relay CR2 is energized. The contacts associated with control relay CR2 immediately change states. Contact CR2A closes and establishes a holding circuit via the normally closed LS2 contact. This holding circuit allows an operator to release retract. Simultaneously, contact CR2B closes and enables the negative ramp generator set to execute a brisk 1 second ramp. Applied voltage to the linear force motor does a relatively snappy transition from 0 to negative 10 volts over 1 second. During this short span, the spool is progressively shifted into the cross-connect position, and flow rate goes from 0 to maximum over the same time period. The cylinder and applied load don't jerk backwards, however their acceleration is pretty abrupt. Let's say the ramp-up event completes and we're at maximum speed even before we hit LS1. The retracting applied load hits LS1. No change in state is observed since normally open contact CR1A is still in the deactivated open state. Leaving the reset region of LS1, LS1 recloses. Another couple seconds later, 2 inches from home, the applied load strikes LS2. LS2 opens and the coil of control relay CR2 is de-energized. The contacts associated with control relay CR2 immediately return to their deactivated states. Contact CR2A opens and removes the holding circuit. Simultaneously, contact CR2B opens and signals the negative ramp generator to execute a brisk 1-second ramp down. Applied voltage to the linear force motor in the proportional valve quickly drops from negative 10 volts to 0 volts over 1 second, and the spool is progressively shifted into the closed center position over the same time period. The cylinder is still retracting, but flow quickly decreases and the cylinder and applied load slam on the brakes. Passing the reset region of LS2, LS2 recloses. No change in state is observed since contact CR2A is still in its deactivated open state. Given this relatively abrupt deceleration, let's say the cylinder and applied load come to a halt just short of full retraction. As previously, our results during retraction are pretty mixed. The acceleration and deceleration was a little too brisk, and the rod failed to fully retract. We're getting closer, but we've still got some work to do. Again, here's what incredibly simplistic graphs of velocity and rod displacement would look like during the extension and retraction phases. Now, velocity quickly increases and decreases during the constant acceleration and deceleration phase produced by the relatively rapid ramping event. Once velocity reaches a maximum, it levels out. Given changing velocity during the brief acceleration and deceleration phases, rod displacement changes non-linearly. Once maximum constant speed has been achieved, displacement increases linearly. Because of the abrupt deceleration periods, note we stop just short of full extension and full retraction. Again, this is an obvious simplification, but you should be getting the picture. Finally, after some more trial and error, let's say we succeed in adjusting the ramp period to something that achieves our desired goals. Notably, controlled acceleration and deceleration, full extension and full retraction, and no pressure spikes. Since 1 second was too quick, let's say 2 seconds does the job quite nicely. Again, this is an arbitrarily generated value for illustration purposes only. Let's start from a fully retracted condition. When operator presses extend, the coil of control relay CR1 is energized. The contacts associated with control relay CR1 immediately change states. Contact CR1A closes and establishes a holding circuit via the normally closed LS1 contact. This holding circuit allows an operator to release extend. Simultaneously, contact CR1B closes and enables the positive ramp generator set to execute a 2-second ramp. Applied voltage to the linear force motor does a relatively brisk transition from 0 to positive 10 volts over a more reasonable 2 seconds. During this 2-second span, the spool is progressively shifted into the fully straight-through position. The flow rate goes from 0 to maximum over the same time period. The cylinder and applied load smoothly accelerate. Let's say the ramp-up event completes and the rod achieves maximum speed just as we hit LS2. No change in state is observed since normally open contact CR2A is still in the deactivated open state. Leaving the reset region of LS2, LS2 recloses. Another couple of seconds later, 6 inches into the extension stroke, the applied load strikes LS1. LS1 opens and the coil of control relay CR1 is de-energized. The contacts associated with control relay CR1 immediately return to their deactivated states. Contact CR1A opens and removes the holding circuit. Contact CR1B opens and signals the positive ramp generator to execute a brisk 2-second ramp down. Applied voltage to the linear force motor progressively drops from positive 10 volts to 0 volts, and the spool is progressively shifted into the closed center position over the same time period. Flow is decreasing and the applied load is decelerating, but it's still extending. Passing the reset region of LS1, LS1 recloses. Given this more appropriate rate of deceleration, several things happen simultaneously. Notably, applied voltage reaches 0 volts. The proportional valve completely closes, flow stops, and the cylinder reaches full extension. The end result being the most ideal of circumstances. 1. The cylinder and applied load have undergone both controlled acceleration and deceleration. 2. Has fully extended. And 3. Due to the gradual and perfectly timed closure of the proportional valve, no pressure spike is observed. This was the original goal of this whole experiment. But wait, there's more. The retraction phase is the same song, only played in reverse. When the operator presses retract, the coil control relay CR2 is energized. The contacts associated with control relay CR2 immediately change states. Contact CR2A closes and establishes a holding circuit via the normally closed LS2 contact. This holding circuit allows an operator to release retract. Simultaneously, contact CR2B closes and enables a negative ramp generator set to execute a 2-second ramp. Applied voltage to the linear force motor goes from 0 to negative 10 volts over 2 seconds. During this span, the spool is progressively shifted into the cross-connect position and flow rate goes from 0 to maximum over the same time period. The cylinder and applied load smoothly accelerate backwards. Let's say the ramp to negative 10 volts completes and the rod achieves maximum speed just as we strike LS1. LS1 opens, but no change in state is observed since the normally open contact CR1A is still in its deactivated open state. The cylinder and applied load continue to retract. Leaving the reset region of LS1, LS1 recloses. Another couple of seconds later, 2 inches from home, the applied load strikes LS2. LS2 opens and the coil of control relay CR2 is de-energized. The contacts associated with control relay CR2 immediately return to their deactivated states. Contact CR2A opens and removes the holding circuit. Simultaneously, contact CR2B opens and signals the negative ramp generator to execute a 2-second ramp down. Applied voltage to the linear force motor goes from negative 10 volts to 0 volts, and the spool is progressively shifted into the closed center position over the same time period. The cylinder continues to retract, however flow rate decreases, and the cylinder and applied load decelerate. Leaving the reset region of LS2, LS2 recloses, but no change in state is observed since contact CR2A is still in its deactivated open state. Given a more appropriate rate of deceleration, several things happen simultaneously. Notably, applied voltage reaches 0 volts. The proportional valve completely closes, flow stops, and the cylinder reaches full retraction. As during the extension phase, the retraction phase was a total success. 1. The cylinder underwent both controlled acceleration and deceleration. 2. Has fully retracted. And 3. Due to the gradual and perfectly timed closure of the proportional valve, no pressure spike is observed. Here's what a simplistic graph of velocity and rod displacement versus time would look like during the extension and retraction phases. Note velocity linearly changes during the constant acceleration and deceleration phases produced by the ramping events. Once velocity reaches a maximum, it levels out. During deceleration events, velocity decreases. Given changing velocities during these acceleration and deceleration events, displacement non-linearly changes. Once maximum constant speed has been achieved, displacement increases linearly. Due to the perfectly timed deceleration period, we stop at full extension and at full retraction. Long story short, mission accomplished. For real this time. Let us review. After 4 repetitions, the punchline of this analysis should be painfully obvious. By adjusting the proportional valve controller ramp generator parameters and observing the results, we achieved our objectives of controlled acceleration and deceleration in both modes, extension and retraction, full extension and retraction, and mitigating pressure spikes. Importantly, all 3 goals were obtained by controlling the proportional valve's actuation. By progressively opening and closing the proportional valve, the cylinder and applied load undergo a controlled acceleration and deceleration, and by perfectly timing the closure at full extension or full retraction, we minimize pressure spikes and maximize travel length. If any of these factors aren't true, our larger objectives will not be fully achieved. Keep in mind, proportional valves are not limited exclusively to applications incorporating linear fluid power actuators like cylinders. They are also perfectly suited to control the acceleration and deceleration of rotational actuators like hydraulic motors. Similarly, by ramping up and down applied voltage to the proportional valve, flow rate is progressively increased or decreased, allowing for controlled acceleration and deceleration and minimizing pressure spikes when a hydraulic motor with rotating inertia is brought to a stop. Consider an extremely similar application in which a bidirectional hydraulic motor is being used to shuttle an applied load back and forth on a conveyor belt. By properly adjusting the ramping time to the proportional valve, the hydraulic motor smoothly accelerates, reaches maximum speed, and when the applied load triggers the limit switch signaling deceleration, brings it to a controlled halt. Before we bring this lecture to a close, allow me to comment on repeatability and system maintenance. Note the proportional valve tuning process necessitated the involvement and guidance of a trained technician and a number of steps. In summary, it took some effort, but now it works, and we can walk away confident we did a job well done. Theoretically, this properly tuned system should repeatedly execute the same sequence over and over again as long as one important assumption is made. That assumption being that no influencing factor ever disturbs the system. A disturbance might be categorized as fluctuations in flow, pressure, temperature, or voltage, or changes in applied load or friction. As we all know, such an assumption is asking way too much of the real world where such changes can and do occur on an exceedingly regular basis. This being said, the system should continue to function ideally inside a range of tolerances. If disturbances accumulate such that the system performs outside this tolerable range, a technician might have to perform the same service over again to retune the proportional valve. Systems making use of proportional valves, especially those subject to a fluctuating environment, may require periodic tuning as part of regular service procedures. Related to some higher level topics we'll examine in later lectures, this necessary involvement of a technician is what is known as a type of open loop control. In open loop control systems, the resultant output is never actually observed or measured by the automated system, but rather subjective human judgment and action are necessary to adjust the system such that these goals are achieved. In contrast, slightly more sophisticated closed-loop control systems automatically monitor the resultant output and can internally regulate their performance to adjust their output to match that desired of it via feedback. By comparing the results to the desired set point, a closed-loop controller can self-regulate its output. In summary, open loop, no feedback; closed loop, yes feedback. We'll examine open and closed loop control of fluid power system actuators in later lectures. Alright, that's about it for our discussion on acceleration and deceleration control using proportional valves. In conclusion, this lecture took a look at acceleration and deceleration control using proportional valves. We learned that controlling the ramp up and down of applied voltage controlled the gradual opening and closure of the proportional valve, and thereby the flow rate and acceleration and deceleration characteristics of the applied load. Additionally, we learned that perfectly timing the closure of the proportional valve, the travel length of a linear actuator like a hydraulic cylinder can be controlled and pressure spike minimized. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.